So in this video we're gonna learn about Kruskal algorithm. So Kruskal algorithm is used to find minimum spanning tree, and it uses DSU topic, or you can say union find. So DSU is a synonym of union find, and we need to find MST. What is a MST? So let's take a graph, a weighted graph. So it is connected to 2, then 3, 4, 5. So like this, we have a graph and it's a weighted graph. So we have to connect each and every vertex. So you can assume you have to go from point A to point B, but there are multiple routes. You have to take the minimum route. So we have to connect A to B uh, from we have to connect each and every vertex while taking minimum uh, weight. So one MST is this, or another MST is this. This is another MST, or another MST is this. So we have multiple MSTs. Sorry, we have multiple spanning trees. Spanning trees, but we have to find minimum spanning tree. Spanning tree means connection of each and every vertex. So suppose we have v vertices, so we require v minus 1 edges, and we have to find the minimum spanning tree. So we have a question. Let's um, first read the problem statement. We have this minimum spanning tree. You have given a weighted and directed connected graph with v vertices and e edges. Our task is to find the summation of weights of the edges in the minimum spanning tree, MST. Graph is represented by urgency list. Each vector represents edge. First denotes the endpoint of edge. Second denotes the weight. So you have given adjacency list like this. So now first learn about DSU topic. So DSU is a very lengthy topic. So we will focus on DSU first. So DSU. So for DSU, we have 0, 1, 2, 3, 4, 5, 6. So we have these nodes, or these indexes, or these vertex. So we have to connect this vertex with this vertex. So first of all, we have to find the representative. 0 is representative of 0, 1 is representative of himself, then 2, 3 is representative of himself, 4 is a representative, or we can say parent. 4 is a parent of 4 means itself, 5 to 5, 6 to 6. But if we try to merge this and this, we will make a group of this and this. So the representative is only one. We have only one representative of this. So uh, 2 will now call to its parent. 2 parent is now 1. So we will change the parent. Then let's connect this vertex with this. So this 3 is in only one group, and you can make a representative of any node. So I am taking 3. So let's take one will call to 1 will call to 2 will call to 1, and 1 will call to 3. 2's parent is 1, one parent is 3. So one way is this, another way is this. We have different ways. So now let's build one another group. So we have taken this group. This representative is this and this. So this is called union. We are making union, or we are forming a group of two different nodes. So we have these two groups. Then we want to make a union of 2 and 3. So we will find parent of 2. Parent of 2 is 1. Then parent of 1 is 3. So we have 3. So for 2's parent we have 3. Then for 3's parent, 3 is also 3's parent. So it matches, means it is already in the same group. It is already in the same group. So what if we want to do the union of 6 and 1? So 6 parent is 5. So then 5 is a parent of himself. So 6 is only reached till 5. Then we have 1. 1 will reach to 3. So 3. The parent of 6 and 1 is different. Means they are in a separate groups and we want to form a group. So what you can do? You can assign 5 parent to 3. 5 parent will now be 3. And now these 5 items is in a one group. So let me show you the code. First we have to find the parent of a particular index. Then if the parent matches, means they both contains in the same group, else we have to form a group. So we are just changing the parent of a current index. So let me show you the code of union find. We have union find and inside this we have a parent array. Initially, every index is a parent of himself. Then we are union, we are taking making a union of A and B and finding the parent of A, finding a parent of B. So in the union function, if the current element is a parent of himself, means this is the representative. So just return the representative and just call the recursive function with the parent himself. If this is not a, if the current index is not a parent of himself, then one optimization you can do. So let's say now we have to find, we have to take a union of 6 and 4. 6 and 4. So 6 will call to 5, 6 will call to 5, 5 will call to 3. So we know 6 parent is 5, but 6 representative is 6. 6 representative is 3. We are only interested in the representative part. So we will change 6 parent to its representative. So now it will look like this. So what if instead of 6 we have 2? So 2's parent is 1 and one parent is 3. But we are only interested in the representative. We want to check if they are in the same group or not. So it will return 3. It will return 3. So we are just directly point out to 3. We are just directly point out to 3. So this will look like this. After finding out the representative, just set parent value of the current index. Just set the parent value of the current index. So that's about the path compression. This is called path compression. This just one word is called path compression. Now let's finish the union part. We have to find union of 6 and 4. So 6 will reach to 3 and 4 will reach to 4. They are not in a same group. So we have to find if this is in the same group, just return if this is a not in the same group. So parent of PA will be parent of PB. Parent of 3, parent of 3 will be parent of 4. So it will look like this. Parent of 3 will be parent of 4. So this is about the union part. But one optimization we can do, we can do a optimization. How? So we have done one optimization till now, which is called path compression, and further optimization we can do is union by rank. So let's say this component, this component, this component, this component. First, initially its parent is 0, parent is 1, parent is 2, parent is 3. The rank, how many nodes it contains, what's the length. So initially the length is 0, length is 0, length is 0, length is 0. Then we will set, we will we will make a union of this and this. And 2 now, 2's parent is now 1. 2's parent is now 1. So the length of this tree is 1. Length of this tree is 1. So it will look like this. So if tree length is 1, suppose we have one different tree So this is a tree like structure. 2, then 3, then we have 4. So its length is 2. So if I insert it here, we want to do union of 1 and union of 3. So there is no harm to point out 0, then 1, because the length is still 2. Length is still 2. The maximum length is still 2. So our benefit is to make parent of this particular node to this node. So we have to do union by rank. What's the rank? If the rank is less, if the rank of PA is less than the rank of PB, so uh, just assign. This is the rank. Just assign parent of PA will now be parent of PB. So simple as that. So let me show you the code. We have a rank, and we are first creating the rank. Then if rank of PA is less than rank of PB, just set PA parent will be PB. If rank of PB is less, rank of PB is less, so just set rank of parent of PB will be equal to parent of PA. Then in this third case, in the third case, is like we have simple set. We have 0, then 1. Its rank is 0, its rank is 1, its rank is 0 also, and the parent 1, parent 0. So you can set parent of this PA, this PB, parent of PA. So this it will now call to PB, but its particular rank now increased. So that tree will look like this. Its rank is increased. So rank of PB is increased by 1, because initially they both rank is same, but now the rank is different because we have this parent statement. So that's about the union find. Now it's time for the Kruskal algorithm. So let me erase. So now let's continue our Kruskal algorithm. So now we are familiar with the DSU or union find. Then we will uh, we will insert each and every edge in our union find. We will insert each and every edge. So what I will do, we have this. So in this, 1 is connected to 2 with weight 2. Then 1 is also connected to 3 with weight 5. Then 2 is connected to 1 with weight 2. But I will not take this because I have already considered this. So there is no benefit of taking this. So just ignore this. So 2 is also connected to 4 with weight 7. 2 is connected to 5 with weight 9. Then 3 is connected to 1, but I will not take this. 3 is connected to 5 with weight 4. Then 3 is connected to 4. So 3 is connected to 4 with weight 8. So it's term for 4. 4 is connected to 2, but I will not take this. 4 is connected to 5. So 5 with weight, 4 is connected to 5 with weight 6. 4 is connected to 3 also, but I will not take this. Then 5. 5 to 4. 5 to 4 is already done. 5 to 5 to 2 is already done. 5 to 3 is already done. So that's about all the edges, and we have to create minimum spanning tree. So I will um, I will add this and sort it according to the weight. So our first element is source, our next element is destination, our third element is weight. So sort it according to weight. So this first this, then this will come. So let me mm, so then this will come, then this element will come, then 6 element will come, then 7 8, then 9. So now after sorting this, we have to check. We have to check. We have this source and destination. Is 1 and 2 connected? 1 and 2 is not connected. Why? Because in the DSU we have these components, and 1 is a parent of himself, 2 is a parent of himself, 4 4 5 5 3 3, and all the vertices is now uh, individual, so we have to connect 1 with 2. We first have to check the parent of 1. Parent of 1 is himself. Parent of 2 is himself, by using just a find function. So it is not connected. So I will use this and connect this. We don't need to connect the graph literally. We are just interested in the weight. So I will just take the weight if this is not connected. Then next we have 3 and 5. So 3 and 5 is not connected, so I will just consider the weight. So the visual, this is just for visualization. The MST is just for visualization. So 3 and 5 is not connected, so 3 and 5 will now connect. I will consider the weight 4. Then 1 and 3 is not connected, it is not in the same group, so just consider the weight. So I've considered the weight. 4 and 5. 4 and 5 is not connected. Just consider the weight. Then 2 and 4. 2 and 4 is in the same group. Our DSU will tell us the parent of 2 and parent of 4 is same. So they are in a same group. We don't have to do anything. We will not uh, we will not take this particular weight, because 2 and 4 parent is same. They are in a same group. Then we have 3 and 4. So 3 and 4 is also in the same group. Then 2 2 and 5. 2 and 5 is also in the same group. We don't have to do anything. So we will not consider the weight. So weight we have considered, we have considered is 2, 5, 4 and 6. So its summation is 17. So we have answer as 17. MST is just a value. So one optimization you can do is this is not connected, this is not connected. 1 and 3 is also not connected. Then 4 and 5 is also not connected. So we have considered this. So we have considered four edges, and 4 edges is enough to connect 5 vertices. Then we will just break out from our loop. We don't have to find more such values. We will just break out and return the answer. So this is just optimization. If our count reaches v minus 1, so just break out and return the answer. So let me show you the code. So inside this we have a Kruskal function, and I am passing adjacency list and n. Then we have edges and we have boolean, so it will tell us whether u and v is connected or not. So boolean, then we have to traverse in the edges, for in the edges. So then u, then v, and this is the corresponding weight. So if u and v is already connected, just continue. If it is not connected, so just add source, destination and weight to our edge list. Then mark u and v is connected, and we have also considered v to u. We will not take v to u differently. After that we just need to sort it according to weight in minimum order, in ascending order. Then we have union find or DSU and an answer to return it. Then we will just iterate in our edges list. So this is my edges list, and I will take each and every edge. I will consider each and every edge. So just check u and v. I have u and v. If the parent of u and parent of v is in same group, means it is already joined, so it is in the same group, just find it. If it is not in the same group, just make it in a same group, and consider the weight, consider the edge weight. as a distance. After that, just need to return the answer. So let's talk about the optimization. We have count and count plus plus. If count reaches n, just break out. We don't have to do anything. We have considered each and every. We have joined each and every vertex. So now let's give it a try, and let's talk about time and space complexity. So first we have this loop, and it will work for v plus e. Then we have collection function. Collection function, in this we have added edges. So it will be e log e. Then we have union and find. So union and find, it will work for log e. So the total time complexity is e log e. So it is same as this is the time complexity. And space complexity, we have this visited function. So instead of visited, and we also have union find, it is n instead of this, and we also have edges. So uh, it will be edges, so order of e. But instead of this, one optimization you can do is, we are just interested in adding, if u is less than v, if there's a edge from smaller vertex to higher vertex, so only consider that. So using this we can optimize it, and let's give it a try. I hope it will work, and I will provide this code in the description box. If you guys have any doubt related to DSU, union find, or this Kruskal algorithm, just drop a comment. And yes, we have successfully solved this question. Thank you all for watching.